Thanks, Dylan, for the intro. And you also might notice that I'm just here alone. Unfortunately, my colleague Alyona is out sick, so I guess it's just going to be me. So when we prepared this talk, we were like saying, hey, we've been working with Timeseries, and it's cool to like show things that work out. But both of us have spent the past 20 years working on this, and we wanted to share a couple of the failures we've seen on the way, because I thought it might be interesting also for you if you're working with Timeseries. About that. So first of all, what are Timeseries? And I can just ask you in the room, like, who of you has worked with Timeseries data before? Cool. How many of you have been to a PyData conference that had a Timeseries talk? Exactly. And that's seriously, that's a problem. And so what is Timeseries data? I'm just making sure that everybody in the room gets it. In the end, we're talking about records of time and a key, so a name of a variable, and the value that is recorded over the course of time. You can see that there in this arbitrary example and in the slightly more real example. And they're nothing new. They have been around, or let's say, used by engineers around the world for many, many years in industrial control systems, SCADA systems. Some of you might have heard this term. They're all around you. And sometimes you don't even realize it. And so where they are commonly found, a couple of examples. Financial data is probably the one that you know the best. ERP systems, so enterprise resource planning, markets, wherever big money is involved. It's interesting what happened in the past, and most importantly, what will happen in the future, because this is where the money is. Second part is, you see this ECG recording. It's about healthcare. It's about consumer IoT. You probably all have an Apple Watch. They're doing time series analytics all the time on the fly. There's also weather data, forecasting of the weather, what will happen tomorrow. These are all dynamic time series models that are happening there. The last part is an example. You've probably all used a Grafana dashboard to get insights about what's happening in your systems. All of that is time series data. But to generalize that, it's in industrial Internet of Things, it's in automation, it's in sensors, it's in robotics. So it's almost everywhere. The thing is, what's so special about it? You've said like you have been to PyData events, but there were no time series talk. Why is nobody talking about it? Is it easy? I personally don't think so. Time series data is special in the way that it has a very high cardinality. So it's typically very, very long series, because if you record something over a long time, then there's a lot of variables in there. The second part is, as you're talking about real systems, there's a lot of noise in there, so it's often noisy, so you have noise problems in there. And when you look at these systems, it's rarely that one single sensor comes alone. They usually come in groups of 10,000, 50,000, or 100,000. So it's easily also a problem to deal with massive parallelity. The other thing is, even if you have a lot of data, it doesn't mean that there's a ton of information in it. If a recording that you take every milliseconds of the exact same value, great, you use up a lot of memory, but the amount of information you're getting is not so much. You could compress it to say the value is 1, and it goes on for the next 6 hours. That has about the same level of information of recording it every millisecond. But that means be very careful about the information you're getting out of such systems. When you're saying, oh yeah, we have 20 gigabytes of data of that machine, does it really tell us anything if it runs stable as a flat line? Often many series in parallel. I've just said the thing machine. Just imagine you run a lot of machines in parallel. If you go to, let's say, a refinery, you can easily have 100,000, 500,000 sensors that are recorded. And if you want to do time series analytics and that, it's a whole different question when you're saying you're just looking at one sensor. The other thing is, typically, time series data have the property that they come in all the time. We record it at a certain frequency, at a certain amount, and here's the thing, it doesn't stop. It's not that you scan a book and you're done with scanning that book. You can do your analytics, run a model, and forecasting it, or so on. Time series have the point that they continue. Meaning, if you take a database dump, you analyze that, you run a model, it's very likely that you'll miss the very recent history. The thing is, as we've seen, this data is almost everywhere. It means the answers are often highly time critical, and also it can mean that the monetary impact of working with that data can be quite huge. And so what's so special about it? Yeah, it has a timestamp, so guess, yeah, you're a time series analyst. But let's get a little bit more serious. Like, why do companies care about time series data? It's basically a part about data-driven analytics. When you want to run your company better, it's typically about factors that are business value driven, like you want to be faster, better, cheaper, or in some cases, happily, they want to be more sustainable. But it's also the external factors that, with uncertainty, meaning volatility in the markets, in supply chains, and so on, the complexity and the ambiguity of events that are happening around you, time series analytics become ever more important. Also, competitive pressure mean you need to get better in what you're currently doing. So time series analytics is yet the next thing, business forecasting and so on. But there's also points like compliance and safety and experience loss in the job market. So let me give you a general overview, and that is nothing that is Python specific, but it has more to do with like the tasks that we're doing and putting them in perspective. Just say over time you record a certain KPI and you have knowledge until right now. Very simple, you can draw this line, and what we often do is we write a report, so we aggregate the data until this point, run some descriptive statistics, add up some numbers and so on. Often people use pandas to do that, and that's fairly easy. Producing this moving average that is drawn there in yellow, a little bit more complicated, but still a fairly trivial task to do. Where it becomes interesting is whenever you want to look into the future. You want to forecast how this series will let's say, proceed in the coming future. This is when you need a model of some way or the other, and this is also one of the reasons why we're here in this room, because this is in the end what a lot of us do when they work with time series data. If you work in financial markets, you want to forecast what will happen next because there's money in it. If you run a machine, you want to know how a certain sensor or the machine will do. This is also where the money is in. But where the real money is in is when you ask the inverse question. You're trying to optimize. You want to bring that certain KPI to a certain goal, and you want to know what you have to do right now in order to reach this goal. Optimization is where the real fun in time series is, and like when you ask our friends in mechanical engineering and so on, this is where they spend most of their time solving optimization problems in direction. The last part I will also not miss out. It's about detecting certain patterns, certain events in there over time. For the examples today, I used a very simple tool to generate time series data. It's my temperature sensor at home. This is not a picture of the actual sensor, but build one yourself. It's a great way of testing out data pipelines and showing how you can miraculously fail at the easiest things dealing with time series data. So I highly encourage you to do that. But now let's come into the topic of today. That is talking about the fail. And I want the fails. And the first thing that I recurrently see when I coach teams at time series projects is dealing with that time series data, we completely forget what is the context of the data we're talking about. We treat it like regular tabular data, a database dump, something we get out of our Postgres, we download the variables, and we don't talk about context. What do I mean with that? Let's start pretty simple. This one here is in this case not my temperature in the garden. This is my oven at home where I bake pizza. And I'd like you to have a guess what is the real signal between these readings that are taken approximately 60 seconds apart. Anyone have an idea? Because it's noisy data. Pretty good. You saw it. It was probably a too easy example because this is the data noise filtered in that case. Pretty simple. Why am I trying to show you that? Just imagine, and it's about sampling and the frequency that you have behind it. Just imagine you would just sample here, 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 and here. And you try to interpolate this line, you could get wrongly the impression that it's flat. Why do I tell you that? Whenever you work with time series data, make sure that the sampling frequency you look at the data in is actually matching the real process that is below it. This is the most common failure I've seen working with people with time series data that don't think about the sampling frequency. But let's turn this around. Every single sensor that we're dealing with comes with their own noise. In this case, I've just taken my particulate matter sensor, 10 micrometers, and just taken that data, but be pretty clear. What I put in there is the error bar that comes from the sensor itself according to the data sheet from the manufacturer. Another thing that I highly encourage you to is when you take time series data, think about where does the error come from for that signal that you're looking about, because no matter how you look at this data, when you resample it, which is what I see a lot of people doing when they deal with time series data, you might, let's say, fool yourself. I've shown you here two possible ways of taking these discrete measurements taken at the given sample frequency, how you could connect them. Just a straight line from point to point, very, very noisy. Everybody will say, hey, no model will be working with that. You could also just say we resample the frequency as it is to instead of every about 90 seconds to every 30 minutes and flatten by that way. But you can immediately see that there's a couple of drawbacks with that. So this line here, this resampling line, will trail the actual measurements. Why is that important? If you take that resampled data and train a model with it, you will fool yourself, because you're off by a certain time frame, because you created an artifact and removed information about that. So thinking about how you can do it right when you are resampling your data, I strongly encourage you to think about what's the error behind. And you see in this case here, it's the red line there that uses the same 30-minute intervals to resample, but the only difference is I don't take every value that is in that 30-minute box and take an average about it and place one dot at a certain arbitrary point in time, but I use an unsymmetrical window in this case that matches the error distribution of the underlying signal. Because I said to you before, particulate matter, the error is distributed Gaussian, and because of that, the right windowing function can make a huge difference when you interpret that line. So when you ignore all of that, you're removing really, really valuable information from the signal that you're treating with. And so taking the signal out of context is something where I say, hey, please don't do that. You make your life subsequently significantly harder. That being said, we're dealing with real data, so often that means you can have massive outliers in that case. But the thing is, finding algorithms how to find out what's true and what is not so easy. We could spend probably an hour or two talking about different techniques how to do that. What I'm just saying to mark something like this, talk to our friends in signals processing, in electrical engineering. They are the experts about that. It's not you as data scientists need to find that out. There's a lot of beautiful libraries to do this. Please don't reinvent the wheel. Read, in this case, sorry to say it, the manual, how to do it right. And please don't just downsample the data. Second part, ignoring the history. I've seen a lot of people in projects when they're starting off with time series data to just say, hey, we treat it as tabular data. There's an entry at a certain point in time, and I can do my calculations exactly the way as I should do. But to remind you of the picture I had in the beginning, if we want to look into the future, we are taking assumptions. If we think about it or not. If we're saying we don't do anything, we take an implicit assumption that everything stays the same. That the system that we're talking about is exactly the same as it was before, which is really the reality. The one thing we can be sure about is that the further we look into the future, taking these implicit assumptions, the less likely it is that everything stays the same. Why am I saying that? Because what people do when they look into the future, they try to do autoregressive analysis. What does autoregressive analysis mean? It's just you look at the data as you have it, just with a timestamp, and you don't take any external information, so additional sensors or so on, into it. In this case, you take an implicit assumption that the signal you are seeing is composed of a trend, of a seasonal component, and some residual, so that's taken together as in this case, a multiplicative operation is going like that. Keep that in mind, because I'll come back to this problem and this assumption later on with another of my failures. Training models brings me to a really, really good point. I've seen or reviewed so many projects where people take the test data or the totally available data and just do a regular train test split. 80-20 is, I think, what most people do these days. And a typical k-fold cross-validation looks like this if you take the sklearn model selection splitting tool. Please don't do that when you work with time series. Please do not. The reason is history matters, and you should do incremental time series splits, because otherwise, what you do if you do this is you have information bleeding, because you want to forecast, but you train this model on something that it already knows about in the future. This is really not great. Please don't do it. A lot of garbage will come out, and the models will even be less good than they already are. Third one, using just a simple standard KPI to evaluate the performance of your models. What do I mean with that? When you work with regression tools and you try to go in the future, mean absolute error, root mean square error, these are the typical things, how you say, hey, I have a goodness of fit and so on. Of course, there's more advanced measures, but these are just two arbitrary examples. When you talk about time series, there are specialized measures that you need to take care of. Because even if your model is just 1% off for every forecast that you have, It really matters if you're having the direction of that error right or wrong. Because let's just say you're in financial markets. You're always 1% off, but you're always predicting the wrong direction. It's a great way to very effectively lose a lot of money. We don't want to do that, so please use specialized KPIs and take them in perspective to make sure that you answer the business questions you have correctly. These are not typically the measures you're seeing in a lot of regression analysis, but please take that step back and ask yourself if you're asking the right question. The answer is, it's complicated, it depends. What I'm seeing in many of the projects I'm in, it's not any of those alone that you take, it's the comparative combination of all of those to say if it's a good model or not. And the choice of model itself, it always, of course, depends. There's a big difference in terms of models that are great into a very short time frame or a very long time frame. That's one thing. But it's not just about the time frame that you're looking at, it's also what is the dynamics that this model can show. Are they able to just give you 1 point every half an hour, or can they capture the entire dynamics of the system? If you're working with heavily downsampled data, it's very unlikely that your model will be able to capture the whole dynamics. So please be aware of that. When you have a complex data preparation pipeline that does complex filtering, you might be applying very well a low-pass filter where you remove all the information about the dynamics, whereas the question that your business is trying to answer is actually a highly dynamic one. So the precision required, I often see teams continuing to work and to work and to work to get all these KPIs better, to make them better and better. Ask the question, what's good enough? Sometimes it's just enough what you have right now and move on to a different problem. The next point is robustness. Is your model and the model structure able to perform well under different conditions? We'll come to that in a second. And the last part is the assumptions and knowledge of the system. If you're going in and saying, hey, I just have the data, I know nothing about the system I'm talking about, it's typically a lot harder to work with time series data than when you have a deep understanding of the system that is behind it. And just a little beam to that, that's exactly the point. You've been probably, when you're working in industry, being asked to give a forecast for the next couple of years. That's exactly the point. The assumptions really matter. I've given you here a couple of popular examples for different model categories that I've seen occurring very, very frequently over the past couple of years. Simple and classic models like the seasonal decomposition, or statistical models like ARIMA and ARIMAX. Put them in two different columns for the reason you can have models that stand for themselves, meaning they just take the variable in question, or ones that use exogenous information, so additional information as well, in order to go forward. There are ones like ARIMAX, or more complex, the bazooka, LSTMs or RNN with Keras that are used frequently. And why am I saying that? The one that I'm often seeing performing the very best for most of the business questions I'm seeing is in the end a linear regression that is smartly chosen on rightly pre-filtered data for the questions that you're asking. Give you the example of predictive maintenance. Just taking, I don't know, the last week of a certain machine, taking a performance of a certain predictor, just doing a linear forecast. It's really cheap to run it, really cheap to train it, and the precision is often better than some of these bazooka models that you see out there. So ask yourself very wisely if it's worth to go down the super complicated route and make sure that, and basically go into a position where you easily can go into, let's say, a hallucination situation, because in the end, whenever you look in the future, you're extrapolating. Make a sure.
Do you mean classical linear regression, or do you mean mixed models?
It can be a mixed model as well. It can be also a very, very simple linear regression on that very function itself. But we can discuss that afterwards in detail. Fail number 4, and I need to look into time, politely ignoring cross dependencies. I said previously that the variables we're talking about are rarely coming alone, and I give you here an example. Spurious correlation, the amounts in the US of spending on science, space, and technology, and the suicides by hanging. Of course, you can make up a story how this is correlated in some way, but why am I showing this example? A lot of the cases you think that observations you have in a certain system may not be correlated at all. Often with time series, especially, you have very limited knowledge. You're trying to describe a system, meaning a black box. You have only a certain number of inputs that you know, and there may be very well more other inputs that you don't know. What does that mean? It means you need to take assumption what happens to those or do surrogate modeling for these inputs in order to understand how these outputs, out of which you also may not know some of those, and you also don't know which of them are feedback to the original inputs. And so, that being said, the cause and effect in such systems is something you cannot ignore. And if you go forward, here's an example from an output and an input in a certain variable. In this case, visually, you'd probably say, yeah, I see this peak up there, and I see a peak down there, and it's slightly time shifted. Great. Input and output. But it points to another problem that often things don't happen at the same time. And if you just go back to this regular pandas data frame, where you're saying, hey, I just have a multiplication of this column and that column, and you have a time frame, hey, we're talking about something different. So that being said, if you want to dive into this topic, which is in the end a rabbit hole, talk to our friends in signal processing once again, because there's beautiful solutions out there for all of these problems, and these problems have been solved many, many years ago. So in that case, it's a fail if you don't look and reuse these materials. Let me give you an example what it means when I say with calculating stuff. Here's a very simple example where this, I don't think this works, where this KPI is just calculated, and I try to highlight this here by 1 hour. If you just do it columnar, you come out to this KPI to 101%, doesn't make much sense. The actual calculation looks like this, but there's a second problem with that. What you can also see from this is not all of these variables are sampled at the same frequency, because you have only discrete readings as we established in the very beginning. So again, be very aware of the assumptions you take when you do such calculations. Do we do interpolation? Do you do forward filling? Do you do downsampling? What is the right choice for the system? Being aware of the assumptions you implicitly put into such operation can make a huge impact on the output that you produce by these models. And the next point is coming back to cardinality. Just if you just sample every minute that variable for 1 year, you get up about a little bit more than 500,000 lines. Not a problem, can fit in pretty much every memory, no databases will have any problem with that. But just imagine you have 5,000 of these columns. It's probably a pretty bad idea to store them in a regular columnar database. That's the reason why other systems exists, to deal with that cardinality, to store them differently. But what does it mean for us here as Python users? One data frame for the whole system where you have your 5,000 variables in is also a pretty bad idea. Narrow down your data sets to what you actually need and be aware of the memory you're using. Not only your CTO will be happy about less of the cloud spending you'll have on your clusters, but you also don't have to wait 6 hours before some of the calculations complete, and you will not use Spark. Be aware of the impact that it has, what type of variables you're using when you're dealing with, in this case, I don't want to use the word big data, but with large data sets in that way. Thinking first about what you're trying to control, to calculate, can actually make a huge difference. Fail number 5, assuming that models are static and you can just deploy. You remember this example I had with the seasonal decomposition? Just imagine we're doing that in the beginning here, but something has truly changed. So our forecast shows that the beer consumption in Australia will straight go up. It totally didn't, because if we just trained our model here, at that snapshot, took a database download, you probably agree that's not a great idea. What does it mean for us in that way? Time series models, one thing is true. If you train a model, you definitely will have to retrain it continuously, all the time, and that has massive impact on the infrastructure you're putting into play. Please don't try to train your time series models offline in a Jupyter notebook. Build automation infrastructure, how you can automatically deploy a new model structure. Find a way how you can robustly train your hyperparameters for the model structure. And most importantly, in a very time efficient and computationally efficient way of how to train your parameters based on the new data that comes in. And I can only repeat that. One does not simply train one time series model. You have to do it over and over again. And why does it matter? Here's an example from one of the projects I've worked previously on. I've worked for not the company that is depicted here. That was just the example package that came up in the Creative Commons. But like airplanes, they have turbines, maybe 2, maybe 4. Turbines work very much the same in that way, but they all come with slightly different initial conditions. They have a different maintenance history, different age, and so on. They have different boundary conditions. They're operated differently, but the model structure themselves and how they break, it's pretty much the same with all the turbines out there. What is our answer if we want to automatically train 10,000 models, retrain 10,000 models once a day, monitor the operation on those? That's not an easy question. I've worked with that customer, and in the end, there's an operational team of 4 people that run the entire operations behind. That means you need a massive scale of operation, but what it also means is you need a super robust data pipeline that addresses the cleaning of the data, that monitors data drift, model drift, and all that stuff automatically. These are the problems that are interesting and where, let's say, taking all these points from these fields together has a massive impact on the success or not success. I have a bonus fail for you. Time is almost up, but it's enough for the bonus fail. And my bonus fail is assuming that time is linear. Sounds funny, but the reality, it is not. Just think about just a couple of weeks ago, we had a time change from summertime to wintertime, which means if you lose local timestamps, yeah, you had the time of 2 o'clock in the morning twice, which may matter for some things, which may not matter for other things. But that's only one thing of the weird things that can go wrong with time. I don't know who of you have heard of leap seconds. Every now and then, leap seconds are introduced, and suddenly you have an hour that has 3,601 seconds. Meaning if you now step by 1 hour, you suddenly have an offset. Pretty not cool. The next thing that is also pretty not cool is it's not just about the absolute timestamps, it's about also time deltas or time spans that exactly produce these problems. Even a leap year can make a difference if you say, oh yeah, every 30 days or every month we do something. The next thing is, we are all Python developers here. The one thing that is absolutely not consistent through all the machine learning libraries is how timestamps are handled between different libraries and so on. So that's a pretty big deal. And the next thing is, even if you know that your local time is there and you know the machine stands in a certain town, be aware, even the assumption that where a machine stands will not change its time zone is a pretty bad one. There's multiple examples of towns that change time zones. I've had that happen, and it was not a great thing to happen. Don't assume anything when you're working with timestamps, but my best practices I can share with you are very simple. Convert any timestamp you're getting at the time of ingestion in your data pipeline into UTC. Please do it. Don't work with timestamps. You'll do so many conversions into sklearn, sktime, and whatsoever, or whatever other library. Please just convert at UTC at ingest. And the second part is, if you even want to be more sure that it works, just convert to Unix time. That's a pretty good choice if you're not working with data before 1970. And the last part is localization to your local time. Do it at the end. I could say in a provial way, hey, let's make it someone else's problem, meaning a front-end problem. But in some cases, it's the same problem all over again. And with that, my take-home messages. Time series are a very special type of regression problem. Pre-processing the data can easily obstruct your whole analysis and change the entire outcome of why you were doing this project entirely. Not because you did a bad job in training your model and validating it, but in the end you failed at the verification, meaning that you built the model right in that way. Great forecasting models often involve domain expertise. You can make things significantly better often if you have knowledge about how the noise is distributed, what the sensors mean, and so on, which in some cases may not be possible. But while there are right first principles, sometimes knowledge from engineering or physics can really help you to make it easier. Storage and retrieval of the large data amounts is often underestimated. We can have a different talk about that. And what happened before also matters. Time series, and if that's the one message you can really take home, is don't just train a model once. A time series model is not static. You will need to do it again. And the last part, it's not always DNS. When working with regression based on time zones, it's always time zones. And with that, thank you very much. Visit us at the booth, and
All right, thank you so much. I think this was a talk that I wish I had had earlier in my career, so I didn't have to learn some of these the hard way. Is there any questions for Sebastian?
Could you maybe say something about quantifying uncertainty, especially in forecasting problems where that's important?
Can you repeat the question for that?
So the question was basically about quantifying uncertainty, and I think that is that more referring to the sensors themselves or more to like the forecasting uncertainty, because both of them are problems of its own.
Yeah, both really, but mostly about forecasting.
Okay. In order to forecast the, let's say, achievable accuracy in a forecasting model, I would highly recommend to first look into understanding the uncertainty that comes from the sensors itself. If you have a 5% uncertainty in the measurement that initially goes in, it is extremely unlikely that you will ever be able to produce a model that is better than this 5%. It sounds so simple, but please don't forget that. And so for forecasting accuracy, what does that mean? If you're now using multiple sensors of their own, and they all have a 5% accuracy, it's not necessary that these errors are additive. There's the Gaussian error distribution with that, so that's the first step to get an idea about the overall envelope, how good can you get. That's the first part about forecasting accuracy. The second part is by the model itself. Depending on which assumptions you take in cleaning the data and or filtering the data, it can either get better in terms of achievable accuracy or worse. Because depending on the time frame you're looking at, the dynamics you're looking at, it again can also get better. The one thing is always true, you will not be able to get better than the Gaussian error distribution. That's just information theory in this very end. I hope that but we can continue this discussion in detail if you want. Yep.
Thanks for the talk and tips. I want to know, do you have any suggestion when we want to do data normalizations when we are working with sequence data? Because I think that it's not like a classic data that's not sequence. That's for instance, we do min-max sometimes when we want to turn a model, like we find the max and mean and then bring everything between 0 and 1. But how is the things working when we are working with sequence data?
Mathematically, you could say you do a work in a different in the end space, because you do a space transformation in that way. That being said, working with just the information where certain maxima, if I understood correctly, maxima and minima are, I've seen models like that working very, very well. The other thing that what I've seen people doing with the minima and maxima problems is with working so-called relative models, which you are basically saying, no matter where I'm starting my forecast, I start at 0, because that's numerically a lot simpler. And you're just saying, hey, I see a trend upwards and downwards, and then I do this back transformation into where the original value was and use that in order to forecast the next value, if that makes sense. But that goes with the same idea, minima and maxima, to say, hey, we're trying to do it in a different space. Also, what may be useful in this minima and maxima point is, if they occur in a certain frequency, think about if you can do your forecasting in Fourier space, which is also often a very great way of simplifying your problem.
Any other questions? Okay, well, let's thank our speaker again. Thank you, Sebastian.
Thank you very much.